lead of this project, along with our colleague Hector Novoa in the UNSA side, who's also in the room. So he can present the current project that we're going to present, and also the team members that who will do the presentation today.
Yes. Hi everyone. I'm Mengye, and as the Victor said, I co-lead this project with the actor Nova, and the title of the project is Very High Resolution Regional Climate Dynamical Downscaling and Hydrological Simulations for Arequipa region. The primary goal of our project is to project what will happen to regional climate and water supplies within the Arequipa region in future changing climate, in particular with the expected increase in temperature. And we do this by performing regional climate model simulations at a resolution that is an order of magnitude higher than global climate models. The simulation also contains a hydrology model component that can project the river stream flow changes, and we consider several different temperature increase scenarios. Today, the three scientists on our team will give a report on recent progresses of our project. And three scientists, Dr. Mengye Chen, and he will present hydrology model simulation results for Arequipa region, and followed by Dr. Xiao-Ming Hu, and who is a senior scientist in our center, and he will present results from the global climate projection model projections. These serve as a baseline that we can compare our results with. And finally, Dr. Yongjie Huang, and he will present results from our high-resolution regional climate simulations. Without further ado, I'll let them to start the presentation. The first, Mengye Chen.
Thank you.
Yes.
Thank you.
Hi, everyone. Hi. I'm talking through the Zoom, and nice to meet you all. And next slide, please. I will present you the results coming from the hydrological modeling.
Just a sec. Something happened with this system. Is
okay.
I'll come back right away.
Right. Yeah, first of all, one of the goals we try to achieve in this project, we try to produce this continuous, near real-time hydrological model throughout the Arequipa area. So there's a couple of reasons why we want to do this, because there's a couple of benefits and multiple things that the real-time hydrological modeling could do. The first is the flood and drought management. So if you continuously modeling the streams using the hydrological model, which that covers every single piece of the river that you're looking at, instead of just one gauge, one location, you know when and where the drought or the floods might happen. So that's one very important benefit with that. And the next will be the water resource management, that you know how much water you're getting. So you're not depleting your water resource in your location, especially for Arequipa area. It's a very dry place. You want to keep your stream keep running instead of use all the water over there. Then the continuous modeling also can help you for the emergency response. For example, there's a big floods coming in. Then you because there's some head time between when we know there's upstream, there's a big floods coming in, there might be a couple of hours that you have some wiggling room in downstream in a village or a city. So if you're modeling that whole region, entire basin, something is coming down in the upstream and downstream, you can have better response to get the people, evac the people to some safer place. Then after that, because you have all the details about how much water you're getting, then you can work on your irrigation scheduling. You can work on, if you have hydropower, you have work on your power generation scheduling. And at the end, you can model how much contaminants spreads over the basin, over your river networks. If you add in the environmental management, environmental module in the model. Just one more click. I circled 3. I can click once. Well, anyway, so I circled the 3 most commonly used benefits of hydrological modeling, which is flood and drought management, water resource management, and agriculture planning that has been realized in real time in the United States and a portion of Europe, and it happens, it been working pretty well. So, being said that, we want to do the same thing in Arequipa region because we do have such success in the U.S. For example, the NOAA has a national water model that been running entire North America, a portion of the Canada and portion of the Mexico plus entire CONUS. Also, the NSSL, National Severe Storm Laboratory, is running the FLASH project, which uses the CREST EFI model that runs in real time too. Again, just let you know that not one model can work perfectly. So what is happening right now is the agencies, the weather service agencies, they use multiple models. They use World Hydro National Water Model. They use CREST at the same time, and they all give us slightly different results. So they have a better idea what's going on in every piece of the country. Also,
Go ahead.
oh, okay.
Yeah.
All right. Somebody mailed me. Right. So also there's a lot of work we have done. For example, that we calibrate the entire CONUS for the hydrological model that is calibrated and it works well. So those data we used can be transferred to Arequipa region. So based all on that, I think we're ready to build this system in Arequipa region too. And moreover, next slide, please. Moreover, we also have some success of projecting into the future by coupling the WRF modeling output with the hydrological models, so we can examine and understand what's climate change impact to the water resources, to the flood and flood conditions. We have published similar studies in the U.S. and hopefully towards the end of this project, we will be able to do the same thing for the Arequipa region. Next slide, please. First of all, let me introduce you what is hydrological model. So basically, hydrological model, we use numerical simulation to find where and how much the water quantity from precipitation to your streams. So it use multiple mathematical models. Well, I would say not as complex as climate model, but it does describe the physical process that governing the movements of the water through the soil to the channel. And on this graph is just a basic demonstration that water coming from precipitation goes into some might be snow melt or glacier, then generate into this runoff, which is called surface runoff, and there's a subsurface runoff, which creates a surface flow and an interflow, which is a subsurface flow. And they all converge into the channel, then creates that waterfall that you see. Now, of course, some of the water will goes to your groundwater. That's basically the total process. Next slide, please. So when we try to apply hydrological model to Arequipa region, there's significant challenges. I have to admit there are a lot of challenges we haven't expect. The first of all is we didn't know how dry Arequipa area is. Just for comparison, if you're living in Oklahoma, like in Norman, our annual precipitation is about 1,000 millimeter per year. But for Arequipa region, a large area of Arequipa is less than 400 millimeter. And unfortunately, for all the hydrological models in this entire world, okay, every single one of them, they are not doing very well when there's not much precipitation. Because the hydrological model was originally, most of them, they are originally to detect floods, which most likely happen to place that's wetter, has a lot of water, and has a lot of precipitation, and they usually most models have very high correlation with precipitation and their the model outputs. However, that's not the case of the Arequipa region. The next slides. And also, Peruvian Andes Mountain and Rocky Mountain and the Himalaya, those three biggest mountains in the entire world, they tend to have very poor performance on precipitation data sets. So while it's understandable because it's mountains, you don't have that much rain gauges. You don't have that many rain gauge cover there because people don't really go there. Then there's a blockage of the radar of the satellites. So none of those areas has a good precipitation data set. And based on the previous study, Arequipa region, the part of the Peruvian Andes is one of the worst performing area when it comes to precipitation data. And if you remember the two slides earlier, that the precipitation is one of the main driving force and the main input of the hydrological model. So if the precipitation data has a lot of bias, a lot of error in those mountainous area, then those errors propagate through the model and create a larger error in results. Next slide, please. So the last but not least challenge is, so let's say Arequipa area is so dry. Then where all those water from? Because the stream is still flowing water every day, right? It's not completely drying out. It keeps flowing. So one the precipitation is not that much. It's the glaciers on the top of the Andes that provides most of the water in the Arequipa region. So that requires that requires the glacier modeling, which is totally another branch of science to study. And most of the hydrological model don't really consider so well on that part. So that's another definitely a big challenge for this project. And also other small challenge includes undocumented lakes, which is our lake information from satellite. Some lake is too small, the satellite didn't pick it up, right? It's undocumented. We don't know how big that is. We don't know how much volume of water it can take. So there's undocumented. And there's some undocumented subsurface water channels and some canals, some underground tunnels that is not reviewed that transport water from one location to another location. But we don't know that information, and we just don't know how that water runs, right? Also, undocumented water withdrawal. Some human withdrawing a lot of water from one place to another, but it's not documented. There's no information for that. That will cause error on the hydrological model simulation. Next slide, please. So to tackle those issues, this is how we do it. So we use the mean model we use called CREST-VAC. We have we had this model developed last year and had a publication about it. And well, if you're interested, you can look up this publication about this paper. So we try to combine the NOAA-MP, which is a very, very complex water balance land surface model that considers the snow buildups and consider the snow melts, which is quite important in the mountains. And we combine the NOAA-MP and the CREST-VAC. Then we put the lake information as the input. We put the reservoir operation information into this as an input in the simulation. So then we run this model. So that's how we tackle all those challenges that we're facing in this task. Next slide, please. So this is more technical, right? So just let you see on the right hand side of this figure, all those dots, those red dots are lakes, right? They are generated larger lakes that satellite can see. There might be a lot of smaller lakes. It's not even up there. And also, the other kind of lakes that is the lakes on top of the glacier, on top of the mountain glaciers. That is just not really observable because it might change from time to time. So that's another thing is missing over here. And you see those green triangles. They are all reservoirs. They are dams. They're operated by the ANA in Peru. They have data that provides to us that shows how much discharge they're releasing every single day. So that's very, very helpful. Without that, this model is not gonna perform anything. So again, so just to let you know, the hydrological model, when it runs at the very beginning, it's completely dry, right? There's no water in the channel. There's no water in the soil. Soil is completely dry. There's no snow accumulation, no glacier, nothing, right? Just bare soil there. So that's not real. So we have to do something to make it more realistic, which we call it a spin up. So step 1, 2 is a spin up process. We use 10 years to produce, to get the channels to have some water in there. The soil has some moisture in there. And of course, very importantly, we try to build a so-called glacier, which is not true, right? It is a accumulated snow. But the glacier and the cumulative snow, they're very different. Glacier because they're so compact, it's ice. But accumulative snow is just conceptual snow. They're different. So I say it's unverified glacier depths because there's no way you can verify that. Even you have the glacier depths there, but the model doesn't really simulate the same thing. Just hopefully there's enough water in a solid state that accumulates in the upper stream. So next slide, please. So let's look at some results. Okay, let's look at some good results. The basin on the northern part of the Arequipa, that basin, it's very natural. I don't see many big cities over there. And I think that's a very popular tourism places. There's big mountains and not much development. So, and that's another thing is true about hydrological modeling. It was more like a natural area. Hydrological model tend to perform good. So now you see those three lines over here that you see this the black line that is observation. That's the observation from stream gauges, and this blue line is the simulation that we try our best. The red line is the simulation we take all the lakes out. We take the lakes out. We take the reservoir out. So basically. So all the results you will see is something very similar that the lake it's so crucial for this region. The lake regulates the stream flow so much. During when it's high flow rate times, it turn down the peak flow, so it doesn't have too much flow that for the model it doesn't have too much flow that scares people. And during those dry times, it creates very smooth base flow that looks very relevant to the reality. Because you see those red lines during those dry time, those streams are just depleted. It's already dried out, which is not realistic. Because you have all those lakes, it continuously supply water to the system, and this is how important those lakes are. Next slide, please. And yeah, so that's the same demonstration that the lake has a very important function in this region. Next slide. So when we come down to the southern basin of this area, which has more development, and Arequipa, the city, is here, you will see a lot of difference. The first of all, in the upper stream, which is this is Sunbai Station, you can see the blue line and the red line, they almost overlapping together. Well, the reason is that on the upper stream of this station, there's not many lakes over there. There's just 2 lakes over there, and then it comes to this station. So the lake, you take out or not taking out the lake doesn't really matter. Then another thing is there's underestimation compared to the observation. Well, first of all, I have to say the observation is not the observation data is not perfect, because you can see there's a straight black line sitting there, so which means there's some errors over there. But also, I would say that there's got to be some underestimation about this snow accumulation over the mountain regions, because we really don't know how much glacier that's over there. Then when you come down to this Kakani Station. The next slide. Kakani Station. Then you see. Well, then I got a little bit question about what happened over here, because you see the black line is completely flat throughout the time. Well, I don't know. It might be a very, very well regulated channel that all the water is in a strict control to be released over here, because it is so flat. Which is based on all the hydrograph I work with, it is very strange. All right, next slides, and maybe we can jump to the slide 17. It's last slide that I have. Yeah. Slide 17. Yeah. So the next step, we gotta couple the WRF model simulated precipitation with a hydrological model. Because right now there's not a good precipitation, data sets in the region, right? There are local precipitation data set like Pascal or Pisco, but they're not continuous. There's a missing data. They only operate for a couple of years, then it stops. So and those global data sets like geodas, like GPM, iMerge, those satellite data, they don't function so well in the mountain area. So on the previous study that I have published, it shows that WRF model simulated precipitation is very similar to satellite observation. So for the continuous hydrological modeling, using WRF simulated climate as a forcing might be one of the options to keep this continuous hydrological modeling going, because there's just not much options out there for this region. And when we have to finish this part, then we'll look in the future. And this is my presentation. Thank you so much.
Thank you, Mengye. Just want to make sure that the slides are okay. Is this?
Yeah. My name is Xiao-Ming. As Mengye just mentioned, precipitation is critical for his hydrological modeling. So my research mostly focuses on precipitation, particularly the interaction between precipitation, clouds, turbulence, and dynamical processes over South America under both current and future climate scenario. Next. If we take a look at the annual mean precipitation and annual mean cloud fraction over South America, we can notice that precipitation and cloud processes are very prominent over South America. Entangled together. So we try to disentangle their relationship. Next one. If we break down the annual precipitation into seasonal precipitation, we can notice that there is prominent seasonal variation. We have wet summer season and also dry season during September, October, November. Such seasonal variation is related to the South America summer monsoon. And also, we can notice that there are two major precipitation regions over South America. One is over the Amazon region, the other is over the Southeast South America. Such spatial distribution is related to ITCZ and SACZ, which is intertropical convergence zone, and also South Atlantic convergence zone. What is ITCZ, SACZ, and South America summer monsoon? Next, please. So basically, the precipitation over the Amazon region is related to ITCZ. So basically, in ITCZ, this radiation Haiti is strong, so there is induced a strong convection convergency in the region. And then over the Amazon region, over continent, the Haiti is even stronger in summertime, so it shaped the ITCZ a little bit south. So over the Amazon region, there is strong local convergency, so which induces the precipitation in the region. And also at the same time, there is a northeast trade wind, which bring moisture from the Atlantic Ocean to the Amazon region to supply the moisture for the precipitation. Once the northeast trade wind hit the mountains, hit the Andes, it will be deflected south, so generate the low-level jets on the eastern side of the mountain. We call it South America low-level jets. So the low-level jets flow southward and meet the southern front over the convergency over the South Atlantic convergency zone, and also bring the moisture to the region, and then generate the precipitation over the basin, and generate the MCS, mesoscale convective systems. Okay, next slide, please. So we try to understand the relationship of all those processes and between the cloud and the precipitation. And so we did a regional climate simulation with different model configuration, particularly different boundary layer turbulent schemes. Here we show the cloud cross section over the Amazon from the YSU boundary layer scheme and also from the ACM2 boundary layer scheme. On the left-hand side is the YSU simulation. So basically, this is the cloud through the day from the early morning to late afternoon. We can notice that in the YSU simulation, the cloud dissipates during the day. But in the ACM2 simulation, the clouds maintain through the day. The difference is that the ACM2 scheme has stronger turbulence mixing, so it transports more water vapor from the boundary layer to the free troposphere. So where it can support the cloud maintenance through the day. And next please. Because ACM2 have simulation has more cloud, so block more sunshine. So the surface heating is reduced. So convective instability is reduced. That's why ACM2 predict less precipitation compared to the YSU simulation. So such interaction between turbulence and clouds and precipitation is disentangled in the region. So that's one of our major scientific finding from this study. This is the interaction during the current climate scenario. We also take a look at the precipitation in the future climate scenario. Next slide, please. We checked the future precipitation projection using the SEMIP6 model data. SEMIP6 stands for the sixth phase of the coupled model intercomparison project. It has about 50 or 60 model, global model projection. Here I show two models from one Canada model, one European model, and the precipitation projection for 2017 to 2080. They have different resolution, but all course resolution from 0.7 degree to 2.8 degree is about 70 kilometer to 280 kilometer grid spacing. So which is very coarse. Next one, please. Here is the projected precipitation change by the SEMIP6 model. And so basically the difference between the future year and the past 30 years. So the Canada model predict more precipitation over Arequipa, and the EC model predict slightly different. If we take a look at the ensemble mean, next page. Here is the ensemble mean precipitation change from the semi-6 model. We can notice that on the right-hand side is the individual model projection. We can notice that the most model predict this is the precipitation change over the Arequipa area. So we can notice that the most model predict more precipitation over the region, with a few exceptions. So the ensemble mean predict global model predict more precipitation over Arequipa. Next, please. The precipitation is highly related to the dynamic field, related to the wind field. So we checked the divergence of wind at 850 millibar. We can notice that in this case, the precipitation region is highly correlated with the divergence, convergence of wind here. So we checked the difference of the divergence of wind from future year and current year. Next, please. So here is the difference, the precipitation change and also divergence of wind change. We checked the convergence of the moisture flux. So on the right-hand side is the divergence or convergence of the moisture flux. We noticed that there is a stronger convergence in future year over the South Atlantic convergence zone. So where we have more precipitation. And also over the Andes, there is a stronger convergence of moisture flux convergence over there. So the semi-6 also project more precipitation over the Andes. And over the Amazon region, there is a divergence of the moisture flux. So that's why it's drier in future year. But note that there is large uncertainties from those global models. They have coarse resolution and from 70 kilometer to 300 kilometer grid spacing. Given the shape of the pool, it's very narrow. So if grid spacing is about 300 kilometers, so the whole pool probably only 3 or 4 grid points. So you cannot resolve the local terrain or local land use. So you cannot resolve local meteorological processes. So we started to do high resolution. That's why we started high resolution. Next one, please. High resolution regional climate dynamics downscaling. We use 3 kilometer to cover greater spacing to cover Peru region. And that's the work Yongjie will present next.
Next slide. Yeah. Hi everyone, I'm Yongjie Huang, and in this project, I may conduct a convection permitting regional climate downscaling over the Peruvian Central Andes, and I would like to acknowledge the all group members from OU and ONSTAR. And yeah, the main motivation in our project is to answer how do flooding events change in a changing climate. And the current resolution of GCM models are too close to restore the local forcing and local weather. And precipitation estimation is generally poor in GCM models, especially over the very complex terrain region. And for example, the Peruvian Central Andes. So, and many studies have indicated the added value of the regional climate simulation dynamic downscaling, especially at the convection permitting resolution. And however, a few convection permitting regional climate simulation were conducted over the South America, and also the weather. And, in this region, weather and climate are strongly influenced by the complex terrain, the Andes, and also the South American low-level jet. And on the right-hand side, I give an example. There's from a published study do a precipitation projection. They downscale the 3 GCM model to the grid facing 50 kilometer and 10 kilometer. And from this figure, we can see increasing the model resolution actually can attend the different size of precipitation projection. So this motivate us to conduct a convection primitive simulation in the Peru region. Next, please. So in our project, we conduct using the work model to do the climate simulation, and we the two domain of model configuration, 15 kilometer and 3 kilometer. And for the historical simulation, we use ERA5 pre-earnest data. And for future simulation, we use a 26 GCM model simulation for our model initial condition and boundary conditions. The physics scheme here we in the domain one we use the cumulus scheme, and for other physics scheme, for example, the Thomson microphysics scheme, MYN PBL scheme, and the unified lower length bit model RRTMG radiative schemes for both domains. And for the simulation period in historical run, we run the model from 2014 to 2019. And for future runs, we run model from 2070 to 2080. And both simulation include 1 year spin up period. Next. So here quickly show some preliminary results based on our simulation. This slide shows the monthly precipitation in historical runs compared to the rate gauge data in Peru. And you can see the Peru, the rate gauge station location in the right figure. And from here's monthly precipitation, we conducted two 5-year simulation using two different PBL scheme, the ACM2 and the MYNN. And we also include the 4-kilometer simulation from NCAR subgroup. And based on from this time series, we can see our simulation using the MYN PBL scheme is consistent and also closer to the rate gauge data in Peru. Next, please. So, and for the future simulation, we used symmetric CCM model. So here's this slide so that global mean surface air temperature and also the precipitation change from the GCM symmetric GCM model. And on the left figure, we can see with the scenario from 1.9 to 8.5. The temperature increase, especially in the middle of 2070s. We can see for the scenario SSP 245, the global mean surface air temperature increase about 2 degrees C. And for the scenario SSP 55, the temperature increase about 3 degrees C. And on the right hand side, the precipitation change. We can see with the scenario from 1.9 to 8.5, actually we can see the precipitation change more complex and also the nonlinear compared to the air temperature change. Next, please. So in our future simulations, we selected two scenarios. The SSP 55 and SSP 245. For the SSP 55 is based on SSP 5 and also RCP 8.5, the future pathway with a radiative forcing of 8.5 watts per square meter in the year 2100. And this scenario represents the high end of the plausible future forcing pathways. And the SSP 245, this scenario represents the median part of plausible future forcing pathway. Next, please. And yeah, here is purely so some result based on using our future simulation. And this figure shows the temperature difference between the future 5-year mean simulation and also the historical 5-year run. For the scenario SSP 245 on the left, we can see the air temperature at 2 meters generally increase about 2.2 degrees C in our 3 kilometers domain. And for the scenario SSP 585, the temperature increase about 3.2 degrees C. Next, please. And so this slide shows the annual mean precipitation in our simulation. The first row shows the annual mean precipitation from historical run and also the SSP 245, SSP 585 scenarios. And from this annual mean precipitation distribution, we can see the obvious different features over the Amazon Basin region. In the future simulation, the two scenarios, there are less precipitation over the Amazon Basin region. And to make it more clear, we create different views on the bottom row. And the first figure shows the difference between the SSP 245 and the historical run. And the second figure shows the SSP 585 and the historical run. And you can see, yeah, see the yellow color means the precipitation decrease, and the green color means the precipitation increase. So in most region over the Amazon Basin, the precipitation decrease, and over the mountain region, there's a location dependent. Some area the precipitation increase, but some area decrease. Next, please. And this figure shows the average precipitation in the fixed region is so on the right hand side. And the region 1 to region 4, the region around the east slope of Andes, and the region 5 is over the Amazon Basin region, and region 6 is Arequipa region. So, and this we can see from this figure in scenario SSP 245, in all this region, the precipitation decreased compared to the historical simulation. And in the SSP 585 scenario, we can see the region from 1 to 4. There's the region around the east slope of Andes. The precipitation increased compared to the historical simulation, but for the precipitation decreased over the Amazon Basin. And also we can see that for the Arequipa region, we do not see the precipitation change a lot. And next, please. So, and further, we also just look at some seasonal precipitation. And first, this slide shows the precipitation in summer. We use the January. We saw the general precipitation in January here, and also we can see the different field between the future simulation and the historical simulation, and we can see over the Amazon Basin, also foothill of the Andes. You can see the precipitation in future precipitation decrease, but over the mountain region, the precipitation generally increase. And next, please. Yeah, and this slide shows the precipitation distribution in winter. And actually, in winter, we can see the precipitation change the size opposite. You can see over the Amazon Basin, the precipitation actually increased compared to historical one. in both scenario. And also in the mountain region, the precipitation decreased. So next, please. So finally, we look at the seasonal cycle of the precipitation in different regions. And here, from the region 1 to region 4, there's the region of the 4 precipitation hotspots around the east road of Andes. And we can see the consistent result for the scenario SSP 585. The precipitation increase in summer, January, and for the scenario SSP 245, actually, in summer precipitation decrease compared to the historical run. And for the Arequipa region, the region 6, we can see the especially for the scenario SSP 585, the precipitation evolution is very similar to the historical run. Yeah, and this here I only saw the very preliminary result based on our future our simulations, and we are continue running the future simulation and also doing the further analysis based on this data set. So next slide. Yeah, and so finally, I would like to acknowledge the funding support from ONSA and also the computing resource from Texas Computing Center, OU Oscar and NCAS Cheyenne. Oh, thank you.
All right. Thank you very much, everyone, for that very extensive analysis of what's going on with weather in now, historical data, and future. Now we would like to open you all participants for comments, questions, and the presenter will be glad to respond to them. We have about 5 more minutes. We can go. Yes, go ahead, Edgar. Very general.
Yeah, we actually in our project we don't do the actually 1 year prediction, maybe just shorten the prediction for the climate. Actually in our project we don't do this the short-term forecast. Our project mainly focus on the future climate change. Yeah, so for this question, I cannot answer. Naturally.
Well, I think that actually you are asking for the future, right? If we expect
Next year.
Next year.
next year?
Next year's.
Okay. The simulations we are doing are for about 50 years from now, due to the climate change. The longer we go, and then we expect it higher temperature increase, and we also expect more change in local precipitation, for example. And that's why we focus on, let's say, 50 years from now. And we are not doing 10 year. And I think at 10 year, there is more, like 10 years from now or next year, there is more interannual variations. And that's just part of the climate internal variations. That's, in a sense, it's not the problem of long-term climate change issue. And the climate model or the kind of weather climate prediction models can try to predict next season, next year's rainfall. Maybe mute.
I'm trying.
Okay.
Yeah. So for next year's rain, how much it's going to rain, and that will require shorter range climate prediction models. Usually, you need a global climate prediction models.
Yes. Yes. Somebody else wanted to.
Andres. Hear me?
Yes, go ahead.
Yeah, I am Andres Equeres from MISA. I have one question. Hydrology have three types of precipitation. First is minimum precipitation. This is important for drought. Second is average precipitation. This is important for design irrigation. Three is maximum precipitation. This is important for flooding. My question is, in this simulation of climatic change, what precipitation stimulates?
Thank you, Andres. I think what we're going to do is pick up those two more questions that are coming in. See if you can take a note and then we respond in groups. Is that okay? We have next Orlando, who hand this up. If you want to make your question, please.
Yes, I would like to ask, according to your results until today, it seems that we do not have enough data to obtain models that explain in a detailed way about predictions for the next decades. What do you recommend? Number, type, and arrangement, location of stations, meteorological stations, maybe in southern Peru?
Thank you, Orlando. Dahome next. Dahome is connecting us with us from Cusco in SAC.
Thank you, Victor, for the introduction. Thank you for the presentation. I have a question. And the presenters say that there is lack. There would be like a problem because Arequipa region is kind of dry region. And my question is, we all know that according to the predictions, the rain will increase in the following years or will be more unstable. And besides that, because it is drained, there is a difficulty for modeling. And also, I think what would be the opportunities, because I think we will need to harvest some water because water will be it is a key tool for the development of these regions. So, in this sense, what opportunities or what ideas for research can be done for the Arequipa region? Thank you.
Excellent. Thank you very much. I also have three more questions in the chat box, but we'll come back to those. Please go ahead with those three questions. Who want to say first?
Got first one. On the screen, there's a question on the twister. So that's tornado?
No, it was a
Yaku twister.
there was a river, right? The amount of rain fell in the coast of Peru recently in the last recent 2 weeks.
Yes, in terms of the rare situation, so that's a flooding case,
Yes.
right? Because we are running the model at 3 kilometer grid station, so we are explicitly resolving these heavy precipitation. So the model itself is capable of capturing the severe events, severe precipitation events. So in the model, we have not looked at that in details yet in the model simulation, but we will. We want to look at the frequency and the maximum intensity and location of extreme heavy precipitation events in, say, Peru and in Arequipa region, say, in the future 10-year simulation, 50 years from now, and we can actually count how many such events occur for different intensities, and then compare that with the such intensity and frequency in the past. So that the model is capable of doing that. We need to actually do the analysis. That's that question.
If you want to respond to the previous questions.
One question mentioned is since observation data is not enough to calibrate the model. Probably he is mentioning about the hydrological model. Yeah, as Mengye probably is the person to answer this. According to his presentation, yeah, it does. If we have more observation data available, it can help the hydrological simulation. For example, there's lake information, glacier information, and that is true.
Yeah, right. Observation, right. So, we didn't use any parameter data from the Peru region, right? We used the data we calibrate in US. We transfer those parameters over to Arequipa. It's not really the lack of the observation. Is almost the observation there. The data quality is we have questions, right? So just now, I don't know if you have seen that. The observation of the stream flow is flat. It's a straight line. It's a very, very tiny little fluctuation over the year, which is it doesn't make sense. I don't know if the data have been modified or or that stream is heavily being controlled. So those things needs to be explained. If those data is not representing the truth or the reality, then there's no way we can use that to calibrate the model. So I think those data quality is more important. There's enough sites for hydrological simulation. There's enough sites. There's enough records. I just don't know how much how well those data are. The data quality is in question.
Thank you, Mengye. I don't know if there is other response. There was one more question in the chat box from hydrology model. What data we consider from the reservoirs?
Yeah. I provided the answer towards the end. For the reservoirs, we need the max design volume for the reservoir, and its actual volume, not exactly that date, but maybe in that same month or the same season of the actual volume when the simulation starts, then the reservoir discharge over the time, which I could find them in the ANA website, which is very helpful. Yeah.
Thank you. Well, I think we responded the questions there. Is there another one? The last one from Carol.
What was 6 years of flow used to implement the hydrological model in Arequipa? Well, the study period is from 2015 to 2019. That was designed the study period of this study. Yes, it can be done longer time, of course, if we want to. well, then again, as it was set up this way. Yeah, it's actually 5 years.
Yes. Thank you. Any final comments?
I don't remember the first question.
Right. I wasn't taking note either, unfortunately. But as I guess to kind of wrap up a little bit, if I can attempt to do, if I understood you correctly, the presentation of the data you've been working on indicates that the data is not consistent and complete for the region of Arequipa. And that needs to be established a system to help this modeling to work. And you also, I think, Mengye at the beginning indicated that precipitation is a fundamental factor, but also glacial melt from the mountains. It's important, and that data is not being. We don't have access to consistent data of that. But also in the model, you show for the future that precipitation is going to increase, the temperature going to also increase, based on the modeling. But if that is continues like that, does it mean that glacier melt will continue, and that wouldn't be a factor in a certain period of time, and then the full system will be tremendously more dependent on precipitation only, no more on glacial melt. That seems to be the concerning part for somebody like me from totally outside of the field. It's kind of what I take from the presentation, and I see the importance of connecting better with the Peruvian government agencies that produce collect the data and work with the data, like Tsunami, right? Jose Luis is part of the team, and others in Arequipa to continue that collaboration, and hopefully this UNSA collaboration be also, right, with full collaboration for both sides to make it more sustainable. And this model, more than modeling, is also, it becomes a system of monitoring what is going as we go. So I don't know, that's kind of what I take from the presentation. Again, if any other comments, if not, we passed 12 minutes over the time. Thank you very much to the presenters and Dr. Ming Hu, who's the principal investigator from OU side, and Dr. Hector Novo on the UNSA side. Thank you for your collaboration work, and we will continue to work on these and report and in some more time. We will have another webinar similar to these in April from another project more related to health that we're working on between OU and UNSA. Again, thank you. Muchísimas gracias a todos ustedes, colegas en la UNSA y en el Perú. Hasta pronto.
Thank you.
Thank you very much.
Thank you so much.
Thank you very much.
Muchas gracias. Hasta pronto. Hasta pronto.
Muchas gracias.
Gracias a ustedes. Gracias por
Recording stopped.